Uh, before I before I delve into the concept of sources of magnetic fields, I will define what the force on a current carrying wire, if you put this current carrying wire inside the region of space where there is a non-zero magnetic field. Suppose you have this part of the region in space, we have a magnetic field. You see these are cross signs. What does this cross signs mean? The magnetic field is into the page. If you see dot like this, the magnetic field is out of the page, because we always need a third dimension to define the magnetic fields. You cannot only have everything in 2 dimensions. This is not possible for magnetic fields. This is possible for electric fields, but not possible for magnetic fields, because magnetic fields always require 3 vectors which are perpendicular to each other. So if you put a wire which has some current, constant current flowing through the wire, and put into a region of space where there is some magnetic field, then this wire will have a force on it. And this force is because every charged particle which is in motion are affected by this magnetic field, and there will be forces, magnetic forces on each charge. So as the total effect of this, you have a wire put into a magnetic field. It will be pulled in some directions which is perpendicular to the magnetic field, right? And also which is perpendicular to the direction of the current. If you put a wire which is parallel to the magnetic field, this wire will not experience a force, because B and the current, or the direction of the velocities of charges, is parallel. But 2 vectors, if two vectors are parallel, their cross product is 0. V cross P, if they are parallel or anti-parallel, it is 0, because V cross P depends on the sine of the angle between them. And if there is 0 angle between them, sine 0 is 0. Or if they are anti-parallel, the sine of 180 degrees is against 0. So they must have some angle other than 90 degrees, other than 180 degrees or 0 degrees to have a non-zero force on it. So the expression for this can be derived as the current that flows through this wire times this S vector. S vector is the displacement of this wire from one end to the other end. That's it. It's the length vector from one end to the other end, and it must be in the direction of the current. If the current flows in this direction, the S vector is the same direction with that. So it is nothing but S cross B, this magnetic field. So there is 2 vectors cross product, and so that means the magnetic force must be perpendicular to these 2 vectors. Whether they have a different angle, different than 90 degrees or not, the force vector will always be perpendicular to S and the magnetic field. All right, so imagine we have a wire which is in irregular shape. What to do then? Well, if it's just straight wire, then it's easy. The straight wire has just a length as the magnitude of this S vector, and you can easily find the force. But if you have a irregular shape, then you can imagine this wire as the sum of small ds displacement vectors, and you find the force on each ds vectors and then add them all. So for only one ds, you can define df, the infinitesimal small magnetic force on it, and express the force in terms of ds. Of course, ds itself is a displacement vector, and it's in the direction of current. And ds cross p is just together with I, is the infinitesimal force on this wire, but only for a small portion. So to find the total force on this wire, you have to take the integral. But if you have a constant current, the current does not change at any part, in any portion of the wire, if it is constant, then in fact, without taking the integral, you can find this force. how do you find this force? Because if you add these ds vectors from point A to B, the result is just a straight displacement vector from point A to point B. That's it. If you can find this straight vector, then that's it. And you just multiply this S vector by magnetic field. As long as the magnetic field is uniform, the magnetic field must be uniform to do that. If it is not uniform, then you cannot do. So as you see here, to find the force, you take the integral. And as I said, if the magnetic field vector does not change at any portion of this wire, if it is uniform, then the integral only applies to ds. But sum of ds is nothing but, as I said, is the displacement vector from starting from point A to point B. It's this vector, the black vector. Okay. So the result is I times S cross P. Well, in that case, remember, be careful. This S vector is not the total length of this irregularly shaped wire. It's just the distance between the endpoints. That's it, not its total length. Okay, because it's defined by the endpoints only. Just think in terms of vectors. You add vectors one by one from tip to tail, tip to tail. So you see these vectors as these small red lines. If you add them all, what you have this vector. We have to add these ds's as vector, not as length. This is the formula. If the formula says don't worry about the direction, you just add the total length, then it's okay. It's something else, the result, but you have to add them as vectors. Okay. Well, the next question is, what if you put a loop into the field? Should you have a force on the loop? It's a closed loop. Zero, because if you start from one point, any point, and the current goes and comes to the same point again, so the displacement vector is zero. Just like in mechanics, you start from anywhere in space, you go around, wander around, and come to the same point again. What is your displacement? Zero. So there is no net force on the loop, which is put inside a constant magnetic field. That means the magnetic field must be uniform. If the magnetic field is not uniform, this is not true. Just like the case of a dipole, remember? A dipole, one plus charge and one minus charge put into an electric field which is constant, will not have an external force, because the plus charge will toward one direction force, the minus charge will have the same magnitude of force but in the opposite direction. So in total, the dipole, which is put into an electric field which is uniform, will not experience a net force. Just like this, if you put a loop current inside a magnetic field which is uniform, there will be no force. But if the magnetic field is not uniform, then you will have a force, not net force. On the wire, we will see these kinds of examples. This is only true as long as you have a uniform magnetic field. All right, so let's